Okay, so in this final worked example, we have a cantilever structure. It's subject to a linearly increasing load. So again, this is a distributed load where the intensity is increasing, in this case linearly, from a value of 0 at point B up to a value of 5 kilonewtons per meter at point A. And what else have we got? We have a load applied at point B, which is an inclined load down and to the right. So it's 8 kilonewtons and it's acting along a line at 30 degrees to the horizontal axis. Okay, and we need to analyze this structure. Now again, let's sort of do our housekeeping. We can recognize that we have a potential horizontal reaction, a potential vertical reaction, and because this is a built-in support, we have a potential moment reaction. So we've got 3 reactions, 3 equations of equilibrium, and so we'll be able to tackle this structure. So the first thing I'm going to do is I'm going to just deal with the distributed load, the linearly increasing load. So this is often referred to as a triangular load. And again, we are going to replace this with an equivalent concentrated load. The magnitude of that concentrated load is going to be the area beneath the, let's say the area of the triangle, or the area beneath the line, the inclined line, which is just the total magnitude of loading. So the area of that triangle would be, let's see, if we were to just make a note here, that linearly changing distributed load, LOAD. So we've got the total area equals concentrated load. So let's call it P. That's going to be the replacement load, or what we replace that linearly increasing load with, and it's going to be a magnitude of 5 kilonewtons per meter times the length over which it acts is 10 meters times 0.5, because it's a triangle we're dealing with, not a rectangle. And so P would equal 225 kilonewtons. Now, for a triangular or a linearly increasing load, what we're going to have is the resultant acting 1/3 the way along the triangle, the height of the triangle, or rather in this case the length of the triangle. So it acts through the centroid of the triangle, essentially the resultant load, which is going to be 1/3 the way along. So let's just simplify this thing. We're going to redraw it as a free body diagram. So we've got our structure, and I'll just draw the structure as a line this time. We have reactions, so let's call that VA, assume it acts upwards. Let's just draw HA, assuming that it acts to the right, when our intuition would actually tell us it acts to the left. And let's just draw on our moment reaction, MA. Let's not be too concerned about the direction at this stage. Now, if we draw on our replacement for the distributed load, it's 25 kilonewtons, and it acts 1/3 the way along. So if our beam is 10 meters long, this is going to be 3.33 meters, and that is where that load is acting. Now, the inclined load at point B is going to have a horizontal component, which let's just draw it in as a solid line, and that is going to be 8 times the cosine of 30, which is going to be 6.93 kilonewtons, and the vertical component is going to be 8. Did I get that wrong? That's actually going to be 8 times the cosine of 30, which is 6.93. Okay, so dealing with the vertical component, we're going to have 8 times the sine of 30, which is going to be 4 kilonewtons. 4 kilonewtons. Okay, so now we have a free body diagram. Let's just label it. That's point A. That's point B. And now we can evaluate our equilibrium equations. So let's look at the sum of the forces in the horizontal direction equals 0. Assume to the right is positive. And what do we have? We've got 6.93 kilonewtons plus HA equals 0, and that means that HA is minus 6.93 kilonewtons. And again, the minus sign here is telling me that HA does not act to the right, but it acts to the left, which makes sense to us because it has to balance this 6.93. And so what we would say is HA equals 6.93 kilonewtons, and then the arrow will indicate the direction that we are intending for it to act. Okay, which is opposite the initially assumed direction. Now let's look at the sum of the forces in the y direction. So the sum of the forces in the y direction got to equal 0. Upwards is positive. And what do we have? Well, we have VA minus 25 minus 4. Anything else? VA minus 25 minus 4 has got to equal 0. Therefore, VA equals 29 kilonewtons. And again, positive number, so VA acts up as we initially assumed. Now, we've got to work at the moment reaction. So the sum of the moments about point A are going to equal 0. We'll assume clockwise is positive. And what do we have? So we have MA, which is the unknown here, plus 25 times 3.33 plus 4 by the length of this structure, which is 10 meters. Now, anything else to consider? No, that's it. That all has to equal 0, and we can solve for MA. So MA is equal to minus 123.25 kilonewton meters. Right, minus, what does that mean? It means it's opposite to the direction that we assumed. And so the reaction force is actually, if I draw on my support, the reaction is actually going this way, which makes complete sense to us because that cantilever, if we think about it, wants to rotate clockwise. All the loading is such that the whole cantilever wants to rotate clockwise about point A, and the resistance to that clockwise rotation must be an anti-clockwise reaction force, or rather reaction moment, MA. Okay, so that more or less wraps up the tester, if you like, to see if you're comfortable with calculating reaction forces. Hopefully at this stage that was all revision for you. So we can now move forward to start thinking about bending moments. So that's what we're going to start talking about now in the next section.